Okay, so the purpose for today actually is to just understand what for we need this subject. Why now? Why do we need it? Do we need it? Maybe it's some kind of bullshit that we don't need, right? What is the difference between modeling and simulation? Because, for example, in Russian, it is the same word. Is there any difference? We will try to understand it during today's lesson. So here you can see a picture of, it's like a description of an expert who has knowledge and skills and in one discipline. It's called Tshaped. You know, for example, if you're very good in something in one discipline, you're very good expert, but you're very narrow, and besides your interest, you cannot do nothing actually. Another kind of expert, it's the one which is called a generalist. That one has broad knowledge, maybe he has some skills in one discipline, but he is not very good in other kind of disciplines. And finally, there is a Tshaped. He has broad knowledge, he has skills in discipline, and he is able to apply it among different disciplines. And I believe and I hope actually that our subject will allow you to become this T-shaped person. I hope that you already have some kind of background, you know. So it's it is master classes. You already have your bachelor degree, and maybe you're very good in programming, maybe in control science, in engineering, I don't know. We will take a look at your results. But I hope that after this class, you will have deeper knowledge and you will be able to apply skills of modeling and simulation in different kind of areas and fields. So our subject is called simulation of robotic systems. Actually, our subject will be much more broader than just robotic systems. We will take a look at simulation in general, especially in engineering fields and engineering subjects. And robotics will be just one of the fields, actually. Because simulation is something very general. You can simulate whatever you want. You can simulate economics, biology, whatever you like. But all the practice, all the project will be in robotics and mechatronics. All right, so what is the purpose of the course? Actually, to have fun. I believe, and I would like to believe that this subject is one of the funniest that you can have as a subject for your specialty, since you will be immediately see the results of your work. I mean, you will going to visualize your robots, your systems, your mechatronic devices, and sometimes, in most of the cases actually, something goes wrong, and it's just funny to take a look at this. How your robot is destroying your virtual environment, how you have created the model in the wrong way, and because of that you see something ridiculous. Highly likely it will hurt, because this subject is not only about pushing buttons in a simulation package, but also to understand the theory. And we take a look at the different simulation and modeling techniques. We'll take a look at basic Euler-Lagrange modeling, and also something which is not straightforward, such as bone graph modeling. We're not going to go into details a lot, because I can have a a course only on bone grafts, like 10 lectures only on bone grafts, or 10 lectures about rigid body motion and kinematics, spatial dynamics, and control. So our task is to touch these topics. I will give you links and references, and if you will be interested in it, you can dig on your own and with your own pace if you actually need it, because you need to spend a lot of efforts, a lot of time in order to be good in it, right? And I hope that all your efforts that you're going to spend here will pay off. Why? You will be able to do something like this after the course. For example, here you can see a 3D printer, a model of 3D printer, and it's actually a project that's been developed by a group of 3 people, and one of them have designed the rigid body dynamics. The second one, he tackled the problem of control system, low-level control system, and the third of them, he tackled the problem of planning, and he wrote the G code. And actually, this model was very, precise. The visualization, it's only one part. Our task not just to create a fancy animation; it's just one of the part. The basics, the essential feature here, essential activity, is to be able to model and to understand the results of your modeling. Is it something that you want? Is it the performance that you want, that you need? Is it a good one? Or maybe it's a wrong one, and somehow you need to optimize it, or to make it different somehow, such as it will be good enough. Another animation here, it's with a galloping robot. It's do not gallop, but it's do some fancy motion. Robot manipulators, and here you can see the actual contact modeling, and we will spend a lot of efforts to do this. Walking robots such as Janssen linkage here, grasping devices, and you can see the interaction of a lot of different pieces with an object. So there are a lot of different contact points, and it's highly under-actuated, and it's tricky to do this kind of animation. Cars, gimbals, and actually I have like more than 100 projects from the previous course, from the previous year, and just impossible to show all of them, but there are a lot of great projects there. In the end of the course, I hope that you will know kinematics and dynamics of rigid bodies. You will be able to you will know actually all about modeling and simulation of complex systems. So you will know about different kind of contact modeling, and you also will be familiar with the robot's control. You will be able to simulate mechanisms, to describe motion of rigid bodies, and actually I believe that you will be able to simulate whatever you want, because the concept that we are going to consider very general, and robotics and mechatronics are just examples of our simulation techniques. And you will be able to do analytical modeling and simulation. You will be able to use simulation modeling tools. It's like the aim of the course to study these topics and to get these skills. All right, let us take a look at your results. All right, so the majority is mechanical design, the second place for the programming, and I'm good at all of this. It's very great that you were great in all of this. Hardware and control. You know, it's very different from something that we had yesterday. And it was very strange to see the results. So here it is the results from the yesterday lesson, and 48% have chosen that they are bad and all of this. I guess they just very shy. All right, so let me now tell you about myself, because the course is designed by me, and it's based on something that I've been done for several years. The very basis of the course is my PhD thesis. I have used simulation a lot during my PhD. And one of the topics was grasping devices. For example, here you can see one of the devices that I developed. It's a grasping device that is able to adapt to the shape of different objects due to the something that we called variable length link. So here you can see a link which is able to extend, and it's completely passive, and it's able to extend due to the interaction with the environment. And the contribution of my PhD thesis was about algorithms and methods in order to synthesize such kind of mechanisms which is able to passively interact and adapt to the shape of grasping objects. And due to this feature, we're able to reduce the number of actuators, sensors, and use very simple control algorithms to do this generally complex motion. And the idea here that before creating a physical prototype, we have created the simulation model. We wanted to make sure that everything is fine and everything is going to work, and only then we have created the physical prototype. It works very fine. So here you can see that it's able to grasp different kind of object with a different shape and mass and dimensions. And here you will be able how it's able to grasp different objects. So here you can see that it's able to adapt, and the link is able to extend. It's one of the earliest prototype. After that, we developed several more advanced prototypes. I will show you later on. But here my point is that first, before creating the physical prototype, we wanted to make sure that it's going to work, and we done it thanks to the simulation. Another example here, it is all about the galloping robots, ledged robots with the passive elements. Those structures is able to gallop due to the resonance-based behavior of physical elastic elements. So there is the springs, and our task was to synthesize the mechanism which is able to use real physical elastic elements, such as the design will be more energy efficient than the galloping robots such as Spot, ETH, Unitree, and other kind of ledged robots that we can see right now. And so we have done the simulation. After that, we have created the prototype. So here you can see how it's able to jump in place. And there you can see it has very complex mechanical structure that allows us to get the resonance-based behavior, and it's able not just jump on a place but also to run. And it's very energy efficient because it's able to restore energy. because there is a physical element that acts like a physical battery of energy. All right, so we now have touched a little bit the topic of simulation. So I believe that you have some kind of intuition about what it is. I didn't give you the definition, but I hope that you already a little bit understand what it is. Let us have now a little practice. Let us decide why simulation is better than a real system, why it is better to conduct a virtual experiment rather than creating a real experiment. All right? So let us create a list of characteristics, features, why simulation is better. Also, you can think about why simulation is worse, because it will be the next slide. All right? So let us divide on groups up to three people. I think 2 people will be okay. So you two, you can divide by the groups on 2, right? And for example, you can create a group of 3, right? We have 5 minutes to create a list why simulation is better than a real system. And the next slide will be why simulation is worse than a real system. All right? So let us have a little practice for 5, maybe 6 minutes. It depends on how much time do you need. All right? So here we will have a list of advantages, and here will be the list of disadvantages. What should I write for the advantages? Cheaper. Yeah. It is cheaper. Modify, yeah. We can modify. Easier. Faster what?
Faster output.
Result. Yeah. So it will be faster to get results. You know, it's arguable. It's not always the case. You know,
can simulate rare conditions.
rare conditions. Rare. How do you spell it? I do not remember how to spell it. Hmm?
Simulation that we can start with ideal conditions and then progress with adding more, for example,
Disturbances.
Noise,
Mhm.
nonlinearities,
Mm-hmm. Okay. Hmm? Repeatability. Mm-hmm. Repeatability. Mm-hmm. We can reduce it, and actually we can make it faster. So we can change time. Yeah. We can make it faster or slower time. Mm-hmm.
You can predict any issues in the system and so on.
Predict issues. Mm-hmm.
we can observe inner states of the system.
Inner states, right.
You can reduce danger also.
Once again?
Danger.
Dangers. Yeah, we can get, okay. Danger, we can get rid of dangerous situation, yeah?
Easier to visualize.
Visualization. Mm-hmm. Is it?
Possibility of being developed, we can develop it, it can be edited and developed easily.
It can be added. right? We can modify it. We already wrote it.
The second one.
Second, we can modify it very easy. Something else? Okay, I think that we wrote here the main topics. So let me take a look at my list. So it's generally it is cheaper to model the virtual prototype rather than create a real one. It's not always the case, but it's the case for most of the situations. For example, if you want to study how an elastic element behaves, maybe you can do the simulation, but it will be not very precise because of the lack of simulation packages. So our simulation packages still under the development, and when we talk about something elastic and materials, for example, we still cannot rely on simulation results. But if we do, for example, rigid something with rigid parts, the simulation can be very precise. So here it's the first one. So the second one, we can bring the states that impossible or difficult to get in a real system. We also discuss it right here, right? All aspects of the experiment are repeatable. We can start the simulation as many times as we want. We can tune some parameters. We can see the results, how the result is changed after our modification. We can control it completely. We can see how one parameters influence the another parameters, and it's much easier to understand the relation in the simulation rather than in real experiment. You can monitor all parameters. It's like you can put a sensor whatever you want. In real life, you need to think, is it possible to put a sensor there, because it has its limitations, dimensions, mass, and so on, and it's not like you can put a sensor in just random place in real prototype. But in simulation, you can get all positions, velocities, accelerations, forces, torques, current, voltages, and any other kind of variable. Time constant is not an issue. If we want to model, for example, a galaxy, it's not a robotic example, but still, if we want to model a motion of planet, in real life it will be pretty long, right? But in simulation we can increase time and we can get our results. Or we can think about another example, a simulation of particles. In this case, we can slow down on time to see how they react. Sometimes we cannot do the experiment for some kind of reasons, for example, because of the moral reasons. It's like we cannot hurt a person with a robot, but if we study physical human-robot interaction and we want to create a collaborative robot, we need to make sure that it will be safe enough. And before to conduct an experiment with a human, you need to make sure that it actually will be safe and you're not going to hurt a person. All right. We have a list of advantages, but what is a disadvantage? What is the main disadvantage?
The model may not mimic correctly the real
Sure.
system.
Model is always model. It's not reality. It do not represent the whole physics. It always in narrow boundaries. It only is able to represent only some fraction of characteristics. What else?
Very accurate simulations are very computationally expensive.
Sure, one of the one of the point in the list that we need sometimes a lot of computer power to simulate, and it will be an issue during our simulation. All right, what else?
Unpredicted situations may happen.
Unpredicted situations. What do you mean?
Something that was not in my consideration while simulating.
Many technical problems would be happening when executing the simulation.
Like
It depends on how, you know, it's not a problem of simulation, it's a problem of maybe a system.
I think the problem is one problem is we try to simulate analog world with discrete simulations, which causes problems.
Yeah, sure. It's one of the problems that I didn't wrote here, but actually what I wanted to tell you that in order to create the model, you know, you need to create something that makes sense. You need to understand fully the physics, and your model should be precise. It should be verified. You know, you can model whatever you want, but it maybe have nothing in common with the reality. And your task is to create the model that is pretty close to reality. And sometimes it's very difficult. In simulation, you can model something that looks very fine in the simulation, but if you then try to repeat the same experiment in real life, you will get nonsense. It's completely different results. So the main problem is the one which is called reality gap. It is the gap in results when you compare the results from simulation in real life. It always be the case. It will not coincide. It will not be identical because the lack of the simulations, especially when we talk about robotics, the way how do we model contact has nothing to do with physics. It just mimics the physics of contact, and it's very different. It gives very different results if you do it with real life. And beside that, another problem is modeling of elastic materials. You know, in most of the simulators, the links modeled as a rigid body. But in reality, we do not have such a thing like a rigid body. All details deflect. If it's a plastic detail, it deflects a lot. If it's the metal part, it's do not deflect a lot, but still it's do deflect. And simulators do not consider this effect. For example, in the model of a grasping device that I just showed you, I modeled in a way such as all parts are rigid, but then I printed the details out of PLA plastic, and the trajectories of end effectors of the fingers were very different because of the elasticity of parts. And it was not so precise as I wanted to make it, right? Also, we can say about this issue in a way, I mean, in the field of synthesis and design, mechanical design, but also in control. For example, now we have a very popular topic, reinforcement learning for legit robots, for example. And due to this idea, we do simulation, we do a lot of simulation, like thousands, maybe several thousands of simulations in a virtual environment in order to educate a robot to operate in the environment, but then when you will use this data for a real robot, it will behave a little bit differently, and it will be a good idea. It will be a good outcome if the difference is little bit. Sometimes it's just huge. And also, as you already told us, that you need a lot of computer power to do simulation. All right.